Hey everyone, welcome to the very first video in our series on the reactions of chapter 8. So this chapter is going to be going over reactions of alkenes. So this is going to be where we take an alkene and turn it into something else. So this very first reaction that we're going to do is obviously going to be doing just that. This first reaction is addition of HX, which is also known as hydrohalogenation. So let's write that down. So this is addition of HX, which is also known as hydrohalogenation. Bit of a mouthful. Okay, so a couple things we need to know about this. So this reaction is going to add HX, which HX is HCl, HBr, or HI across a double bond. And we'll see exactly what that looks like in a second. And additionally, this is also a Markovnikov reaction, which we will also talk about. This reaction also forms both enantiomers, which is going to be something we're going to be seeing quite a bit. And then finally, rearrangements are also possible. So these are the important things for this reaction, okay? So let's just do an example. So all I do is take an alkene, and then over the arrow, I'm going to put HX. So HCl, HBr, HI, any of those. I'm going to use HCl in this case. And all that happens is that the hydrogen and the chlorine are going to get added to each of the carbons that were originally in the double bond. So the double bond goes away, and a hydrogen and halogen gets added to each of the carbons. So now you're probably wondering, well, where does hydrogen go and where does chlorine go? Because, you know, in theory, I could add hydrogen here and chlorine here, or I could do the opposite, right? I could add chlorine here and hydrogen here. So which one of these is right? Well, it turns out that this one is right. So then the question is, why is this one right? Well, that one is right because of Markovnikov's rule. So that's what I mean whenever I say that this is Markovnikov reaction. So Markovnikov reactions are reactions where if I'm adding a hydrogen and something else, the hydrogen goes where there's more hydrogens. Okay. So if I look at this carbon here, this carbon has two hydrogens on it, and this carbon has one hydrogen. So then where's hydrogen go? Well, it goes where there's two hydrogens instead of one, right? So that's why hydrogen goes here. So that means chlorine has to go on the opposite carbon, so it goes there. So that's why that's correct. So now I'll write my product over here. So I get chlorine here, right? And then I also get both enantiomers as well. So I'm forming a chiral center. So I'm going to get the chlorine on a wedge and the chlorine on a dash. Okay. So that's it. That's this entire reaction. The only caveat, well, I guess there's two caveats to this, really. The first caveat is that I can have rearrangements. So that means hydride shift, methyl shift, ring expansion, anything like that. So if I take this same thing and use HCl again, then that means that I get chlorine here. Okay. So I get chlorine there. So why? Well, it's because there is a hydride shift, right? So there's a hydride shift in this reaction. So in order to understand that, we're going to have to look at the mechanism. But what I want to do first is look at the mechanism of the one that we just did a second ago. Okay, so let me scroll down a little bit so we can do this mechanism. So I'm going to do the mechanism of the first one. and then we'll worry about the second one. So I have my HCl, and this is an important mechanism that I would definitely know, by the way. So I have my HCl, and these electrons in this double bond can act as a base. So these electrons are going to take a hydrogen off of HCl, and then the chlorine is going to keep the electrons, okay? So then I know where hydrogen goes because of Markovnikov's rule, right? Hydrogen went here, but we don't draw it because this is line angle. So that means that I got a hydrogen here, but my double bond's gone now, right? So that means that this carbon just lost a bond. So that carbon is positively charged, okay? That carbon is positively charged. So I form a carbocation, which this is also why Markovnikov's rule is a thing, right? So right now I've formed a 2-degree carbocation. You can imagine that if I added a hydrogen here, then I would form a 1-degree carbocation, right? So obviously, if I added a hydrogen where there's less hydrogens, then I would form a less substituted carbocation, which is why Markovnikov's rule works. Okay, that's the reasoning behind Markovnikov's rule, is that if I add a hydrogen where there's more hydrogens, then I'm going to have a more stable carbocation. All right, just food for thought. Okay, so now I just formed that Cl minus, right? So chlorine just got a minus charge from the first part of this mechanism. So now chlorine is going to come in and attack this positive charge. And then I'm done. So I get both of these enantiomers. And that's it. It's a whole reaction. Okay. So now let's take a look at this other mechanism for this second one here, so we can see that hydride shift. And like I said, we can have hydride shift, methyl shift, any kind of shift in this. Doesn't matter. Ring expansion, anything. So be on the lookout for that. But this is one example. So again, first step is the same. Double bond takes hydrogen, chlorine is gone. And then I get my positive charge here again, right? Because that's going to be that carbon lost a bond because hydrogen went to the other carbon, right? And then I also have Cl minus, okay? So now if I look at this and I take a hydride from this carbon and move it here, right? Then I get a positive charge on that carbon, which right now I have a 2-degree carbocation. So if I moved that hydrogen, then I would get a 3-degree carbocation, right? So that means that this is going to be favorable. It's going to want to do that. So we're going to do a hydride shift. And then we are going to form this carbocation with a positive charge there in the middle. And then finally, that chlorine is still floating around. So chlorine is going to come back now, and just like it did earlier, it's going to attack the carbocation, and then I'm done. That's it. And I have my lone pairs around it as well. So that's the mechanism for both of these. I don't think that this is too terrible. These are pretty short mechanisms compared to some of the other ones that we're going to be seeing eventually. So remember that I can have any kind of shift in this, so you need to watch out for that. Other than that, I think there's only one other thing that I want to mention for this. Well, there's two actually. So the first thing is that you'll notice on this first example, I drew the chlorine on a wedge and on a dash, but on the second one, I didn't worry about that. So why? Well, this carbon right here, right? And obviously as well, this carbon here are both chiral centers, right? Those are chiral centers. So those two molecules are enantiomers of each other. So then I have to ask myself, is this carbon here chiral? No, because in order for something to be chiral, it has to have 4 different groups around it. Well, this and this are the same group. It has 2 ethyl groups on it. So that means that this is not chiral, right? So I don't have to worry about drawing the enantiomers because that molecule does not have an enantiomer, all right? Okay. So there's one other thing that I want to mention about this. So let me get rid of these two examples, and then I will do one other example here. So the two that we just did were alkenes that were unsymmetrical. So one carbon was less substituted than the other. You can imagine an alkene like this, like this one, right? Where it's completely symmetrical, right? So it doesn't matter. Markovnikov's rule doesn't apply because I have one hydrogen here and I also have one hydrogen here, right? So that means that regardless, I'm just going to get, and we'll put this through with HBr. I'm going to get the bromine on either carbon. So I get multiple products in this one, right? So I get bromine here, but I also get bromine on the other carbon, right? So whenever I have something that's symmetrical, like this alkene is, then I get bromine on both carbons. Also worth mentioning that I do get the enantiomer of this one as well, because this is chiral. So I get the enantiomer of this one, but this is not chiral, so I don't get an enantiomer. So in total, I get three products. Okay, I get this on a wedge, this on a dash, and then I also get this one that is not chiral. Okay, so you have to think about this in terms of symmetrical alkenes and unsymmetrical alkenes, and then you also have to think about this in terms of the mechanism as well. Okay. So I think that's all we'll mention about hydrohalogenation. Well, this version of it at least. There is another version of hydrohalogenation that I think is important. That is a variation on what we just talked about that we should mention. And so this is a very specific one. And so this is addition of HBr in peroxides. So addition of HBr in peroxides is a anti-Markovnikov reaction. So this reaction is anti-Markovnikov, okay? And that means that it's going to be the opposite of what the Markovnikov rule was. Okay, so we'll take a look at that in just a second. So let's say that I have this same one. So we just saw this one earlier, right? And so now this only works with HBr. So I have HBr, but instead of having nothing on bottom, I now have peroxides, which is H2O2. There's other kinds of peroxides as well. Just anything that has O2 in it basically is, for our intents and purposes, will be peroxide, but H2O2 is going to be the one you're going to see most likely. So now, instead of what we saw earlier was Markovnikov, right? So this one was Markovnikov, where the bromine added to the more substituted carbon. In this case, it's anti-Markovnikov, so it's going to do the opposite. So bromine adds there. Okay, so the bromine is going to go where there is less or more hydrogens now, right? So the hydrogen is going to go where there is less hydrogens as opposed to more, right? So this is the opposite of Markovnikov. It's the opposite of what we just saw. All right. So just be able to recognize that and be able to know that. You know, same thing if we had, we'll do one more example of this just to kind of hammer it home. So if we had this ring, then we put it through with HBr and H2O2. Then we have this carbon versus the bottom carbon. Well, bromine is going to go on the less substituted carbon, which is going to be this one. And that's it. Okay, that's all we have to do. So we don't have to worry about a mechanism for this one either. It goes via a free radical mechanism that we don't need to know. So that's all to mention about this one. So, but it's important to know because sometimes people will miss the H2O2 or they'll forget what H2O2 does. So that's why it's important to know what this does. So that way, if you see it on the exam, then you'll know. So you need to know whether or not you're doing just a regular addition of HX or whether you're doing addition of HBr in peroxides, because that's going to give you a completely different product. Markovnikov versus anti-Markovnikov. Okay. So this is everything for hydrohalogenation. So hopefully this was helpful. In the next video, we're going to be talking about hydration. And then we're going to get on to a whole bunch of other reactions. So hopefully you'll stick with me. I appreciate you watching, and I'll see you in the next one.